Have you ever looked up at the night sky and wondered, if the universe is so big, where is everybody? This simple question lies at the heart of one of the most fascinating mysteries in science, the Fermi Paradox. It challenges our assumptions about life, intelligence, and our place in the cosmos. The Fermi Paradox is named after physicist Enrico Fermi, who reportedly asked during lunch one day in 1950, "But where is everybody?" He realized that, given how huge and old our galaxy is, intelligent alien civilizations should have had more than enough time to arise and spread through the stars. On the one hand, the numbers look promising. Astronomers estimate that the Milky Way contains hundreds of billions of stars, and many of those stars have planets. A decent fraction of those planets may be in the so-called habitable zone, where conditions could allow liquid water and potentially life. If even a tiny percentage of those worlds produced intelligent, technological civilizations, our galaxy could be teeming with life. On the other hand, we see nothing. No obvious alien spacecraft in our solar system, no massive engineering projects visible in the sky, and no confirmed signals from advanced civilizations. This clash between high expectations and zero evidence is the Fermi Paradox. To understand why scientists think intelligent life might be common, we can look at a famous idea called the Drake equation. It is not a precise formula, but a way to structure our thinking. The equation breaks the problem into factors like: how many stars form each year in our galaxy? What fraction of those stars have planets? How many planets might be suitable for life? How often life starts, becomes intelligent, and develops technology? If several of these numbers are even moderately large, the result is that there could be many civilizations in the Milky Way right now. Yet, despite decades of listening for radio signals and searching the sky, we have no confirmed detection. That tension, between a universe that looks like it should be full of life and a sky that feels completely silent, is what makes the Fermi Paradox so intriguing. One class of solutions says, maybe we are special. The rare Earth hypothesis suggests that Earth-like planets with complex life are extremely uncommon. Yes, simple life might be widespread, but the long chain of events leading to intelligent beings, like us, could be incredibly unlikely. Think about Earth's history. Life appeared relatively early, but complex multicellular organisms and intelligent tool users took billions of years to evolve. Some scientists argue that certain evolutionary leaps, like the rise of complex cells or the development of intelligence, may be so improbable that they almost never happen. If that is true, we might be one of only a handful of technological civilizations in the galaxy, or even the only one right now. Another twist on this idea is the Great Filter. This is the notion that there is some extremely difficult step in the path from dead matter to galaxy-spanning civilization. The filter could be behind us, meaning that the hardest steps are already past, and we are unusually lucky. Or it could be ahead of us, meaning that most civilizations self-destruct or fail before they can spread into space. Another set of explanations says that space exploration and colonization might be much harder than it looks on paper. Even if intelligent civilizations arise, they may never spread far beyond their home systems. Interstellar travel demands enormous amounts of energy and time, with ships crossing distances measured in light years and dealing with radiation, failures, and the challenge of sustaining life for centuries. Some researchers have modeled how a spacefaring civilization might spread through the galaxy. Under optimistic assumptions, a determined species could, in theory, colonize the Milky Way in tens of millions of years, a blink on cosmic timescales. But if civilizations are not aggressive colonizers, expand slowly, or prefer to remain in small, stable regions, the galaxy could remain only partially settled for very long periods. In that scenario, it is possible that we simply live in an untouched, quiet neighborhood. A different perspective suggests that the universe might be only just becoming friendly to complex life. Early in the galaxy's history, frequent supernovae, gamma-ray bursts, and unstable environments could have repeatedly wiped out life before it had a chance to get going. If conditions have only recently stabilized, humanity might be among the first wave of intelligent civilizations to emerge. Some explanations are more psychological or sociological than physical. The zoo hypothesis suggests that advanced civilizations know about us, but deliberately avoid contact, much like people observing animals in a nature reserve without disturbing them. They could be watching our development, waiting for us to reach a certain level of maturity, or simply agreeing not to interfere with less advanced societies. Another idea, sometimes called the dark forest scenario, imagines a dangerous universe. In a dark forest at night, every creature must stay silent, because anything that reveals its position might be hunted. Translated to cosmic terms, this means civilizations could be afraid to broadcast their existence, worried that some hostile power might attack or destroy them. If most intelligent species adopt this survival strategy, the galaxy would remain eerily quiet, even if it is full of life. It is also possible that their communication methods are simply beyond our understanding. We currently search mostly for radio signals or certain types of electromagnetic emissions. An advanced civilization might use technologies we do not recognize, frequencies we do not monitor, or communication strategies that leave no obvious trace. To us, they would be effectively silent, even if they are talking all the time. Finally, there is a humbler answer. Maybe the universe is noisy with signs of life, but we have barely started to listen. The search for extraterrestrial intelligence, or SETI, began only in the 20th century, and our instruments cover a tiny fraction of the sky, at limited frequencies, for short periods of time. Expecting definitive answers so soon might be like dipping a glass into the ocean, pulling it out, and concluding there are no fish because the glass is empty. As telescopes improve and new missions search for Earth-like planets, technosignatures, and biosignatures, our picture will become clearer. Future observatories may detect atmospheric gases that hint at life, or strange energy patterns that suggest artificial activity. The Fermi Paradox forces us to confront big questions. If intelligent life is rare, then our responsibility to protect our planet and our civilization is enormous. If the great filter lies ahead, we need to understand what threatens long-lived civilizations, climate change, war, uncontrolled technology, and learn how to avoid those pitfalls. If we are early, we might be among the first storytellers of the cosmos, setting the tone for those who come after us. And if the universe is full of quiet neighbors, each watching the sky in silence, then our decision to speak or to stay silent could shape humanity's role in the galaxy.